Hey, welcome to Transformations of Functions. I guess you're actually building up quite a few skills here working with functions. Transformations, what could that mean? Well, somebody said I needed to have a transformation of my face, but I didn't do it. What does it mean? It means changing the appearance, doesn't it? And so that's what we're going to do with the functions now. And they come in two different types, transformations or changing the appearance of a graph, and therefore needing a different formula for the function. And I suppose over here you can see, if we think about starting with the blue one, all the other three are transformations which don't change the shape of that blue initial one. And these are called congruent transformations. It's an identical or congruent figure produced by the change. Congruent or Pearson, and this is going to be based, this presentation, as the others have, on Pearson's textbook. Pearson calls it a rigid transformation. Rigid because the graph stays rigid or fixed. Here's another one where you can see the blue one's gone to the red one, and there's been no change in shape. It's a congruent or rigid transformation. Here's another one. The blue one's gone across to the red one. Oh, but what about this one here? The blue one's gone to the red one. There has been a shrinking. There's a change in shape here. So this is a non-congruent or non-rigid transformation. So we're going to look at all of these types of transformations in this next section. So let's come down with me here and have a look at what Pearson say about this. When you're using a graphics display calculator, it's helpful to know where to expect to find the graph, some understanding of the function, so that if it's been transformed or changed to change the formula, that transformation will occur somewhere else on the window perhaps. And the ones we're going to be looking at in this little part of the course here are translations, where we move all points on the plane a certain distance in the x and y, or reflection, where we might use a line on the plane like the x or y axis as a mirror and reflect it across, or stretching. So they're the ones we're going to be looking at. And of course the translations and reflections are congruent or rigid transformations, and stretches are non-congruent. When you stretch the figure, it actually changes shape. So they are the ones. All right. And it does help us realise that a lot of functions are intimately connected to each other. They are only transformations of a basic shape. So that's a real big advantage in doing mathematics, in trying to understand those connections between functions. All right, so let's have a look at getting into some of these, and before we do that, Pearson's has listed here 8 functions which we might consider our basic tools. They are the functions with which we're pretty familiar at this stage. And we could play with them and have a look at transforming them and understanding what's happening in certain transformations. So the first one is a constant function, y equals c, or fx equals c. Obviously, as you go along the x-axis here, the function takes its constant value. There it is there, a c value, whatever c might be. And then the identity function, y equals x, that straight line, so that if you put in 1 into the function, you get 1 out. That's why it's called the identity function. Put in 2 into the function, you get 2 out again. And then the absolute value function. We actually haven't plotted this much. This is a new function to most people at this year 11 level. And that is saying, well, when you find the absolute value of 1, you get 1. Absolute value of 2, you get 2. And when you have the absolute value of -1, the absolute value, or the distance from O, is still 1. When you put in -2, the absolute value of -2 is just 2. Because absolute value, remember, means the size of the number. So it's easy to see where it becomes 2 straight lines there, if you like. The squaring function, or the quadratic function, y equals x squared, looked at that in many different ways in junior maths and middle school maths. So f of x equals x squared, we're pretty familiar with that one. Square root function, we've started to see that in this course already. There we have it existing only for x greater than or equal to 0, because you can't find the square root of a negative. No, you can't go over there. Can't find the square root of a negative on the real number plane. All right, so then x cubed, have you seen this one before? 1 cubed is 1. 2 cubed is off the scale, is 8. Neg 1 cubed is neg 1. Neg 2 cubed is neg 8. Okay, so you can see how that works pretty well. 0 cubed is 0, so it goes through there. That's what's called a point of inflection, or a change of curvature of the graph there, and we'll look at that function later on, much later in the course. Reciprocal function, reciprocal meaning 1 over, and we've seen in domain and range problems that this does mean a change, or you need to look at the restricted domain because you can't divide by 0. So x equals 0 is not in the domain of this function, so in other words, it can't touch the y-axis. That's an asymptote. It's not in the possible set of x values or in the domain. And then the inverse square function, 1 on x squared. So we might use some of these functions and try to transform them, change their shape or their appearance, and look at what happens to the function as we do that. All right, well, let's start the ball rolling here with translations. Now, translations, we're translating something. We're just moving it, all points on it, in the same way, either in the x direction or the y direction. So in this one, what we're looking at is from this graph, from this little GDC shot, we're looking at moving x squared, that's the one in the middle there, either up or down. So let's have a look at moving it up for a start. Here's y equals x squared. So when you square neg 2 down here, you get 4. So let's then add 3 to it. So it will move up to 7. Can you see that adding 3 after you're squaring it is a simple move in the y direction? And when it's a move like that, we call it translating, moving laterally or across. So here, when x is 1, y is 1. But if we add 3, it goes up to 4. When x is 3, y is 9 on x squared. But we'll go up to 12. So no change in shape. It looks like it does. The red one looks to be narrower, but that's because its fat part has moved off our view window. It's really the same shape. We're just moving up and losing the top fatter part of it. So translations are congruent or rigid transformations or changes of a function. And over here, if we have a look at x squared, take 2, the red one, then x squared, when we square it, over here, 1 squared is 1 on the blue one, but then we take 2, and so that point goes down to neg 1. When we square 9 on x squared, square 3 on x squared up here, we get 9. But if we take 2, go down to 7. So that's a vertical translation. And you can see that the number on the end that's been added to x squared indicates the size and the direction in which that graph's going to move vertically or parallel to the y-axis. All right, have you got that one? That one's not too bad. Let's go down and have a look at the summary of that. So if you start off with a positive that you're going to add to the function, then it's going to go up k units. If you take that positive, then it's going to go down. That's pretty commonsensical because you're actually adding that value to the y point that you're mapping onto. All right, let's see what we can do in the x direction. So here's a few graphs. We're trying to move or translate the function this way this time. In the x direction, a translation parallel to the x-axis, or in the x direction. And here's x squared again, always a good one to use at this stage, because students have done a bit of work with this, you've all done a bit of work with this in middle school maths. Okay, so let's say we want to move it over here, 3 units to the left, no up and down movement, no y translation, just a movement across, translation of the x by -3. Well, the interesting thing is the formula becomes x plus 3 all squared. So we change, because it's an x translation, we change the x term by adding 3. But we get a -3 shift. Hey, that's the opposite sign. That's interesting. We're going to look at that later on as to why that might be so. So if we look at y equals x squared, square 3, you get 9. Now, if we put 3 in this function here, x plus 3 squared, then what are you going to do? Well, that's going to give us a different value altogether, and we're going to be over here at x is -3 for the vertex instead of at 0. So the graph is going to actually shift backwards if we are going to add 3 to the x value before we square it. So it's going to move to the left, going to the left there. What about if we have x squared over here, the blue one again, and we do x take 2 squared? So here we are, if we put x is 0, and then put in this function, take 2 squared, we will have the value 4. Okay, so 0 now becomes 4. It was 0, 0, and the value now becomes 4. So the graph is actually moving to the right, which is the opposite sign to that's in the formula for the function. So have you got the idea there? In a minute, I'm going to ask you to see if you can see why that works, and we'll study it in a bit more detail mathematically. Let's move on and have a look down here at a summary, and we've got our horizontal translations. Now, horizontal now means in the x direction. Okay, so in the x direction, which means this way. All right, so if again you're talking about a positive h value and you take it away in place of x, look at that now, f of x, instead of x you've put x take h. So it actually moves at h units to the right in a positive direction, even though you took that negative constant away. And if you put plus h in place of x, x plus h in place of x, it actually moves at h units to the left. So that's in the negative direction. So there's the movement is actually opposite direction to the sign of the constant. Opposite direction to the sign of h. Now we really do want to investigate perhaps those two as to why that happens. Okay, well let's come down and perhaps do a little bit of investigation. If we took y equals x squared, as we have been before now, that's a little bit of a rough graph here. Okay, so can you understand that y equals x squared looks like that? If every time you calculate that you add some number, then all of those points, the x squared values, will go up by whatever that is. They'll all have 2 added to their y's. Go up. I think you can probably see that one. And if you had y equals x squared take 2, after you've calculated x squared, and that's getting this point, you have to take 2. So it's going to be below. This number down the end is going to be subtracted from the y coordinate there. Okay, so I think you can probably get some sort of feeling as to why the addition of that number at the back of the x squared term is going to move it up and down in the y direction. What about the other one though? Y equals x take 2 squared. This moves in the positive 2 direction because we've replaced x by x take 2. How would you think of that? Well, let's think of this point here, which is 1, 1 on y equals x squared. Now if we take x as 1 and put it in this function, x is 1 and we put it in y equals x take 2 squared. It's 1 take 2 all squared, which is still 1. If we put in x is 2, y will be 2 take 2 squared, which is 0. So here now, so 1 is still 1, but when we put in x is 2, the y is 0. Put in x is 3. Let's do it. Y equals 3, take 2 squared, comes to 1. So this is 1. So see what I'm doing? I'm plotting some points over here for x take 2 all squared. And perhaps I should be putting these in red there. So when I put in x is 4 over here, y equals 4 take 2 squared equals 4. So here y equals 4, 1, so it's up here somewhere. Can you see what is happening? I need a much bigger number to put into x take 2 because I'm subtracting this 2 away. A much bigger number to get that value 4 than what I did need. When did 2 become 4 on x squared? Here it is. Here 2 becomes 4 on y equals x squared. But we need 4 to put into this function to get that 4. Okay, so here looks like a scale's a bit out here, doesn't it? Really say if this is 4, hang on, let's get rid of this. If this is 4 here, then we said this value was 4. So we're needing larger x values to produce the y. That is, we've got to go further this way to get our curve like that. It's actually been moved this way. Why? Because over here in this function we need larger x values, because what are we going to do? Because we're going to take 2 away from them before we square them. So we're taking 2 away. The x value has to be plus 2 larger, so that when it's squared it gives the previous result. So the whole graph is over here. It needs bigger x values. So it means it's going to be moved to the right, because you're trying to compensate for taking away 2 before you square it. Back in the blue one there, y equals x squared, you just squared the straight x. Now we're going to take 2 away from it before squaring. So to get this shape we had before, we're going to have to use bigger x's. That's trying to get some gut feeling. I was going to put in some transformation equation proof, but I don't think for standard level we're going to do that. It's a bit heavy. So that's a sort of an informal discussion of why a vertical translation that's in the y direction just follows the sign of that constant down the end. It follows the sign of the constant. And in an x translation or a horizontal translation, it's the opposite sign to the constant that has been added or subtracted within that x term. All right, let's go on and have a look at some examples. We're going to do some problems now. So here we have the graph of root x. It's been moved and then moved again. let's see what we can do. Well, here the first movement is being translated 3 units to the right. So therefore we know the function, because it's translated in the x direction, the x term changes. So y equals root x changes because it's an x translation. So instead of x being moved plus 3, it's the opposite sign. We'll have take 3. Now it's translated up 1 unit. This is this last graph here, gone up 1 unit. So that is a translation in the vertical direction, the y direction. So what we're going to do down here is add 1. Remember, that's the notion in the vertical direction. The direction of the translation is the same as constant added. So y will be root x take 3 plus 1. Or you might like it to write it as 1 plus root x take 3. And you can check that all out by drawing it on the graphics display calculator. Okay, let's look at another one. Here's another one, the absolute value function. So the absolute value function actually lives up here, doesn't it? Lives up there. So it's been moved. Given that it's down at -2, -3, it means the x movement is -2 and the y movement is -3 because this vertex has gone down there. Okay, so let's take the function and we're going to move it in the x direction 2 units to the left. That's -2. So we will have a sign of +2 in place of the x term. Then we're going to move it 3 units down, right there, see it's over here. And if we move it 3 units down, that's in the y direction, we're going to have take 3. We don't reverse the sign of the vertical movement, if you remember. All right, you could do them in reverse order and you would get the same result. Leave you to perhaps play with that. But just remember now, in the y direction or vertically, you add or subtract at the end of the expression, the end of the function statement, down the end, and it's in the same direction as the movement. If you're moving in the x direction, that's horizontally, what do? You, again, add or subtract from the x in f of x, and you do the opposite constant to the direction. Okay, trying to put it in words there. So that's what we're doing. So up here we want to move -2 in the x, so we change the x term from absolute value of x to absolute value of x plus 2. We change the x term by adding a constant with the opposite sign to the direction in which we want it to move. All right, study that. You might have to rewind the presentation and look at these examples again. Let's move down now and do another congruent transformation, and that's reflection. So what we've got here is a graph of x squared, and we're thinking about the x-axis as a mirror. So you know that when you look at a mirror, a point on your nose appears the same distance the other side of the mirror, and so on for all points. So they are directly across, perpendicular to the mirror. Each point has what we call a mirror image. So this is now what happens. X squared has to go, this point has to go opposite. Got to be the negative equivalent straight across that mirror. So you'll multiply the whole function x squared by -1, neg x squared. So that's a reflection. And if we did it back again, we would multiply by -1 and get positive x squared. So the idea is that all the positives at the top become negatives. But therefore the general rule is y equals f of x becomes y equals neg f of x. It's got to go across the x-axis. Let's look at it down here. Some actual examples then. So here we are. Here's x squared. And if we reflect it in the x-axis, 2, 4, equal distance the other side, here we go, comes 2 neg 4. Neg 3, 9 will become neg 3, neg 9. It's got to go as far behind the mirror, which is the x-axis, as what it is in front. So you're multiplying by neg 1. The function change will be from y equals x squared to y equals neg x squared. So in general, if we've got a blue function there, a point up here has to go the same distance the other side, no x movement, just across the x-axis. And how far behind it must it be? Well, if this is f of b, whatever that is, then this has to be the negative equivalent, neg f of b. So the new function statement is this one down here. Y equals the negative of f of x, because it will make a point plot on the opposite side of the x-axis, and that's what we want with a mirror. All right, the image is the same distance the other side. So that's the effect of a mirror. Let's do some work with that. And go on now to looking at what if the y-axis is the mirror. The y-axis is the mirror. Let's take the square root of x, take 2. And let's go and find an image point of that same distance the other side of the mirror. Oh, the y won't change, but the x will be neg 11 up there, because this x was plus 11. This x is 6. Go the same distance the other side, or the other side of the mirror behind the y-axis, it'll be neg 6. So what's happening? The x value is changing its sign. So in the function, in place of x, you put neg x. So this one had x. The mirror image replaces x by neg x within the function, not the negative outside like it was for the reflection in the x-axis. All right, so in general, a point up here on the function that's going to be reflected goes across and is an equal distance the other side of the y-axis, because we're using the y-axis as mirror. And so A becomes neg A. And B down here has to go the same distance the other side of the mirror, neg B. So what are we doing? X has become neg x. So into the function, to get a reflection in the y-axis, we'll put neg x in place of x. All right, so we've got some reflections now, and let's have a look at summarising that. And you might make some notes from either the podcast here, from these blue strips, or directly from Pearson's textbook, because they have summarised the interesting things in the blue strips. So here, if you multiply out the front of the function by negative, it's going to reflect the graph in the x-axis, right? Because it's going to start either above the axis and go below, or vice versa. Multiplying y values by negative makes them go on the opposite side of the x-axis. However, if you put a negative x in the function, then it's going to be reflected in the y-axis, because instead of operating on one side of y, that may be the positive, if you put in neg x, you'll produce points on the other side, and in simple terms now. All right, so what about some exercises? What about this function up here? Find the function h of x that is a reflection of g of x in the x-axis. So here's the function 2x squared, take 6x, 2x cubed, sorry, take 6x squared plus 3. And if we reflect it in the x-axis, then points up there go down there, points down here go up there. So can you see there's the original function, and it has. That's gone opposite there, that's gone up there. All points are reflected, so that's gone down there, and this has gone up there. All points go on the opposite side of the mirror. This time the mirror is the x-axis. So what will be the formula for the new function? Well, all the positives become negatives and vice versa. So what is the rule? H of x on reflection in the x-axis will become the negative of that. Okay, and so your new reflected function, call it h of x, is multiplying the whole function by -1, because that will make any point up the top go to the bottom, any point at the bottom go to the top, changing the sign of that y value by putting, here it is here, a negative in front. Okay, is that okay? Let's have a look at a reflection in the y-axis. So let's take the same function. So here this function was 2x cubed, take 6x squared plus 3. Starting there again. This time we want the y-axis to be the mirror. So this point is going to go over here, go across that way. Then right on the mirror, that won't change. This point will go across equidistant behind the mirror, and so on. This point goes to this point. So we're going across in the across the y-axis an equidistance behind it or in front of it. So see this point here on the black one will go to that point there. So they change sides of the mirror. Like when you're looking at a mirror, the point on the end of your nose appears to be the same distance behind the mirror as your nose is in front of it. So how do you do that? Well, do you remember? You put neg x because you want points over here to go there and points over there to go there. So you replace x in the function by neg x. And what's the notation? Here it is here. How do you do it? Well, instead of 2x cubed, it's 2 times neg x cubed. Instead of neg 6x squared, it's 6 times neg x squared. It's going to produce a graph which is on the opposite side in x-land. Go from the positive x values to negative by replacing x in the function by neg x. So your final function would be this thing here. Okay, so you could check that on your calculator and draw all these. The Casio give you the same sort of screen here as what Pearson's have used, which is the TI. All right, let's come down. We're getting there, and all the transformations so far have been congruent transformations, or what Pearson's call rigid. There have been no change at all in the shape of the graph. So now we're going to look at, and you might read this up here, pause the presentation, read it. We're going to talk about non-congruent or non-rigid transformations. We're going to try to stretch or shrink the graph. You've seen some of this before, particularly in x squared land. That dark one there is y equals x squared, and as Pearson's are talking about here, this is 3x squared, and then the last one down here is a half x squared. So you already learnt that, the effect on y equals x squared of a coefficient a. What does a do? We used to say it changes the steepness. Here in IB we're going to say it's a vertical stretch, or vertically shrinking it if you like, and we're going to use that sort of language. So here we are y equals 3x squared can be obtained by vertically stretching the graph by a scale factor of 3. Why? Because it's multiplying by 3 and it's stretching up. So we say it's stretched by a factor of 3. If we look at a third x squared, oops, sorry, I put a half there, misread that, so that should be a third here. A third x squared. Then what are you doing? You're shrinking the graph by a scale factor of a third. It's flattening, it's shrinking down, if you like. It's not as steep, not standing up as much. All right, so that's the idea, that's the language that we'll be using. So let's have a look at that now. So this is in the vertical direction. So what are we doing? We're taking a function, let's take x squared, and we're multiplying the whole function by 3. What's it going to do? Well, when x is 1, usually y is 1 on x squared. So now y will be 3. When x is 2, y is 4 on x squared. Now it'll be 3 times 4, right up here at 12. Why? Because look at that 3, multiplying the final y value by 3 will stretch all the points up. Now, when x is 0, y is 0. And 3 times 0 is still 0. So 0 stays the same. This is a constant or invariant point. This is constant or doesn't vary, if you like. And so all the other points, however, will, and up it goes. So it is going to be stretched. So in general, if you start off with a function x f of x, and then you multiply that function out the front by an a, it is going to stretch it up. Well, that's only if a is greater than 1, isn't it? It's going to be stretched up by a factor of a. Here it is here. So it's stretched by a scale factor of a. We can see, because it's gone up, that a here must have been bigger than 1. 2, 3, 2.5, but not a half. That will shrink it, won't it? Let's have a look at that. So down here, when you look at x squared, and you put a third in front of it, 9, when x is 3, y is 9 on x squared. Now you're putting a third in front of it, shrinking it down to the number 3. When x is 3, y is only 3 in a third x squared. When x is 2, y is 4 on the graph of x squared. But now, if you multiply it over here by a third, when x is 2, it's shrunk down to y is 4 over 3. You multiply it by a third. So in general, over on the right here now, when you put x into the function f of x, you plot the point, and it's going to go downwards by multiplying by this a if you have a fraction. So it's going to be a shrinking by a scale factor of, what, 1 on a, if you like there. So here, a is less than 1. That's a fraction. So we're going to have, well, if a is a scale factor, we really should say if a is a fraction itself, a scale factor of a, because a will be itself a fraction, a half or a third. So you don't actually have to put 1 on a in that context. All right, so fractions shrink it. Numbers bigger than 1, stretch it. And you can see why that's going to happen. So let's sort of summarise that now. So this is vertically going up and down. If you've got a number bigger than 1, 1.5, 2, 2.5, and you stick it in front of f of x, you're going to multiply all the original y values on the plot by this bigger number. It's going to vertically stretch it by a factor of a. If a is a fraction, that is a third, a half, something less than 1, then when you multiply in front of the function there by a, it's going to vertically shrink it by a factor of a, where a is actually a fraction. That's going to be a third or a quarter of its original size. It's going to be flatter. Now you knew this from quadratics, where we had y equals ax squared, and if that became 2x squared, 3x squared, 4x squared, we knew it stretched up and was steeper. So it's an extension of that earlier work. All right, let's come down and have a look at a horizontal stretch or shrink. So you might realise, of course, if it's going to go horizontally this way in the x direction, then we're going to have to change the x term. And so the a, instead of going right out the front, has to be put in the function instead of x, ax. So for example, let's say we're going to do a stretch by putting into f not x but 2x. So back in f we're going to change the function by putting 2x. Here it is here. Put 2x in place of x. So it's 2x squared. And in place of x there, 4 times 2x. And so our final function is this thing here. And you can do that on the calculator. So x squared take 4x is this one. Sorry, here's the... I made a mistake there. This one here, the black one, is x squared take 4x, the dark one. And then when we stick 2x in there, we get this function here. So here's a repeat. This is the original function. This is the image. So what are the two windows? We'll have a look. When x is 4, y is 0. That's on the original function. When x is 4, y is 0. But when is y 0 on the transform function, the one that's been stretched in the y in the x direction here? Well, you only need x is 2 to get y is 0. So here, this stretching and shrinking has actually caused this to move in, so that you are actually getting the 0 position on the x-axis at an earlier value, so it's gone back. Okay, let's have a look at some more down here. Okay, so what we've got is multiplying the x variable by a positive number and putting it in front will cause it to be transformed or to shrink. So that shrunk, didn't it, by 1 on a. So if we put in 2x, so a is 2, that will imply shrinking by a factor of a half. So where you have 4 naught, you will go back to 2 naught. Okay, so it's going to shrink backwards there. There we have it. It's going to go back to 2 naught, because if putting a 2 in front of x actually is going to shrink it. So in general, if we have a function y equals f of x, and instead of x we multiply the x by a of x, then everything's going to occur earlier. It's going to occur at an eighth of x. Over here, remember, when x was 4 in the original function, y was 0. But because we put 2x in front, now that same point's going to occur earlier at a half of 4, a shrinking factor of a half, because that a is 2, so the shrinking is a half. Okay, let's do one more. If we have a fraction in front of x, so here we're going to put a half x in there and substitute that into the function. So let's start with our function and put a half x in place. There's our new function, a half x squared. Take 4 times a half x. So here is our original function. X squared take, oops, hang on, no, that's wrong, that's here. This is our original function in dark. Change the scale here, so that's 4 and 0. See down there, x is 4, y is 0. And if we put a half in front of x in both the x positions in the function, here's our original function, but here is our image. It's flattened out. This is the image, what's happened. This is when you put a half x in. So because now you need a value of 8 to get y, it's not, we're way out here. It's actually been stretched by a factor of 2. So it's the opposite effect, isn't it now? When you put that number not out the front of the whole function, as in vertical stretching and shrinking, but put it within the x term. Here we are, we put it within the x term, x on 2. A half in that position actually causes the function to be stretched in the x direction. Okay, let's have a look at a couple of examples down here. Well, here we are. We're going to look at a being positive but less than 1. That's a fraction. We're going to put a fraction in place of the x term. It's going to be a fraction like here it is here. 1 on ax. So let's have a look. So x squared take 4x. Oh! Who want to comment on this? I think Pearsons have mislabelled their graphs here. They have, haven't they? X squared take 4x is this graph over here, see? Going through 4 naught. And x on 2 is this one. It's stretched it. Stretched it by a factor of 2 because we've put a half x in there. Actually, so they've mislabelled this in this particular case. So the new function should be this one here. It's been stretched out. And we see it over here. If you have any function and you put ax in there and a is a fraction, it's going to stretch it by a scale factor of a. So this is moving out to there. So a fraction in front of x actually is going to move the function out further. Okay, it's going to be x on a, but that's a bigger number because a is a fraction, and it's going to go out there. So here it is. If you have a fraction, it's going to stretch it in the x direction. So when you change the x term in the formula, here it is over here. Let's come back over to this one. When you change that x term by putting in a fraction times x, it's going to stretch it out in the x direction. So we can stretch it up, we can stretch it wide, and we can understand a little bit now of how to get the formula for those functions that have been stretched. Or if we have got a formula that's been changed and we can identify that change, we can predict what the graph might look like. Okay, that's a lot of work there. We have translations in both directions. We have reflections in the x-axis and y-axis, and we've got stretching and shrinking in both directions. Okay, so let's have a look at a summary here. Horizontal stretching and shrinking of functions. So if a is bigger than 1, so that's 1.5, 2, etc., the graph of f of a of x, so we're changing the x term that we put in the function by multiplying it by 2x or 3x or whatever, then that's going to move it horizontally. So we've changed the x term, so that's in the x direction, and that's going to shrink it. Okay, so what we're thinking is here, if you have a graph and let's say, what have we got? We might say we've got this thing, and you're putting in 2x or 3x, it's actually going to shrink in. It's going to shrink, it's going to come back this way, because the number in front of x here is bigger than 1. If it's a fraction in front of x and you stick it in there, it's going to stretch the graph. It's going to broaden it this way. Not shrink it, but stretch it, depending on the value of a, if it's a fraction now. So this is horizontal movement, or shrinking and stretching, by changing the x term that you substitute into the function. Okay, so down we come. Let's have a look at some examples here of the stretching as we did for the others. The graph of y equals f of x is shown. It's not a function that we're familiar with. Let's see if we can sketch the graph of these changes. So we're multiplying the function by 3 right out the front. So that is a vertical stretch of 3. So let's look at this. 1, 1 has to go to 1, 3. Neg 1 goes to neg 1, neg 3, multiplying it all by 3. Any point on the axis, the function value is 0, so that stays as 0. 3 times 0 is 0. So this 0 here will stay there. So 0 here will stay there, because what we're doing is multiplying the original function value by 3. If the function value is 0, like where it cuts the x-axis, it won't change. So we can draw a graph based on those few points. The zeros, that one, that one, that one, and the 2 key turning points, that one, that one, vertices here. Okay, let's look at the next one, a third f of x. So we're still doing this in the vertical direction. So here is our function, I'll put it underneath. 1 was 1, so 1 now is only a third. But this is shrinking it, because we're multiplying by a fraction in front. So here, neg 1 was neg 1, now it's only a third. The zeros stay the same, because a third of 0 is 0. So they all stay the same. You could actually do this here. 3 in the parent function is neg 1, so here it's neg a third. So it's shrinking. If you're multiplying a function out the front by a fraction, then it's shrinking it in the y direction. We're shrinking it this way, in y land. Let's keep going. What was the next one? F of 3x and f of a third x. So let's go down to f of 3x. Oh, we've changed the x term, so that means we're moving this way in x land. We've changed it in the x direction. So when we stick 3x into the function, it's going to shrink it in this direction. So where it was, let's take 1, 1, 1, 1. Now the 1 occurs at a third the value. So instead of up here it was 1, 1, it's now a third 1. You've got to find, make the x value of each key point a third of what it was. So here it was neg 1, 1. If we go back up here and look at the parent, neg 1 gave neg 1. Now an x value of only neg a third gives neg 1. So we've got to compress it this way by a third. So where it cut the x-axis here at 2, go back up here, that's the original parent function, it now cuts the x-axis at 2/3. All the key points on the graph have to have the x value at which they occur being a thirded, right? Because we're changing the x value here in a horizontal or x direction shift by shrinking or stretching. Okay, so let's put a fraction in there now. Come down to this one. Let's put a fraction in place of x in the function. Now this will stretch it. Instead of cutting the x-axis, what was it? It cut at 2 before. Now it's going to cut it 3 times at 6. It was 1, 1 before. Now it's going to be 3 times the x value. It's going to be 3 before you get the value 1. And it was neg 1 before. So now to get neg 1, it's got to be 3 times that value. It's neg 3. Hang on, we'll just get this right now, neg 3, 1. So here we want the value, the neg 3, 1. All right, so do you get the idea there? Let's go down and see if we can have a look here at another variety of problem. Describe the sequence of transformations performed on the graph to get this one here, graph of x squared, and just to get that one and see what we get. Okay, so if we do that now, let's have a look. So here 4x squared take 3 from x squared. What's been done? Well, the x squared's been times by 4, so that's going to give us with a vertical stretch with a scale factor of 4. So here it's going to look like this one here. Instead of 1, 1, back on this one, it's 1, 4. Okay, and so on. So that's stretching up because you're multiplying x squared by that 4. You usually start with a function and work out. So it's been multiplied by 4, and then it's had -3 subtracted. So when that's outside the function, not within the x term, then it goes down, -3. So that's a vertical translation equal to the sign, remember. All right, let's do another summary here. When combining two or more transformations, the order in which they are performed can make a difference. In general, when a sequence of transformations includes a vertical or horizontal stretch or shrink, or a reflection, it might make a difference because you're going to change things in a different order, and so you have to check that. Mixing up congruent and non-congruent transformations, things that change the shape and things that don't. So, summary of transformations, what can we say? Here they all are. So you might make a note of this when you add or subtract from the function, a vertical translation. When you add or subtract from and change the x term to a horizontal translation opposite to the sign. And here, multiplying by a negative, reflection in the x-axis, putting a negative in x in place of x in the function, a reflection in the y-axis, and then these two being stretches or shrinks in the vertical and horizontal direction. Might be worthwhile making a note of this table and just checking that out. All right, let's keep going now, because here's your big chance. I think there are a few problems here. I think we go down to 23, yep. So we go down to 23 here, and it's a chance for you to perhaps have a look and then rewind the presentation, at least back to that summary. These are all like that last example, where you're trying to identify what's been done. Has the x term been changed? Has the whole function been multiplied or something? And so on. And then as we go down here, we've got some functions there where we're trying to identify the formula. So these are our functions that we had summarised before, our basic tools, and so you're going to try to predict what the formula would be for each of those under the transformations. I think this is an obvious one over here. There's a reflection or something going on there because the absolute value function was up the other way. So you might have to go back and look at those basic tools, our functions from before, and then we've got some down here. All right, so you can pause it at any stage here, toggle backwards and forwards to look at the problems. I'm going to display the answers here in small sections here. So just noticing, unfortunately, the way I've done this, they're in batches, so we've got 1, 2, 3, and then 4, 5, 6 in that group. So have to toggle a bit. Let's go down and display those first 6 then. There, I can pause that, and then again the same thing here, 7, 8, and then 10 and 11 on the other side. I have to toggle around, and then 9 down there, 11 and 12. So they're in columns, because this was the way it was set up in the answers of Pearson's. Very nice solutions here for you to look at. Let's go now to 13, 14, hang on, we'll just go there. 13, 14, 17, 18, 19. But you'll have to toggle, we'll do the rest of 14 here. Put in that 14 and see if we can get 19. No, not quite. To do that in a minute. So as we go down, the rest of 19, come to 15 there. Okay, got to do it in small pieces, giving you time to toggle backwards and forwards through the pieces. And I think that would then cover all of those. Of course, you can use your textbook that hasn't got fully worked solutions, but the e-book does have. If you go to the left-hand menu down to additional resources and go to the PDFs, the questions there have a PDF icon, and that accesses the fully worked solutions as we've got them here. All right, well, I hope you enjoy that. I'll leave you with the problems back up here, perhaps. It's a place to leave it. And have a go. Enjoy yourself. You actually are building up a lot of skills, which is excellent. And now it's a matter of taking some notes, either from the textbook, those blue sections I've screenshot here, and so that you can remember the various operations. All right, well, have fun, work hard. You need a lot of practice here. Do all these problems. And we're well through this first topic now, and the last two parts are really quite a bit easier. They're a bit of a reinforcement of things that you've seen before. So I look forward to seeing you in the next presentation. At the moment, cheers from me.